3, 2, 1. All right, our next topic deals with the half-life of radioactive isotopes. Now, we talked about radioactive particles and the substances that emit them. It turns out that each one has a different period of time in which half of it decreases. We talked about half-lives way back in chapter 14 when we dealt with rates of reactions. And in first-order reactions, which is what a radioactive isotope decay is the amount of time it takes for 50% of the material you had to start with to decrease. And then a second half-life would be 50% of that 50%, which is 25% more decaying. And then 50% of that 25%, which is 12.5%, decays. And keeps going on and on and on. And in theory, it keeps going until you're down to one atom and then it breaks down, but actually it kind of stops before that. But regardless, the period of time for each half-life is different all the way across, but the process of determining it is exactly the same. So let's take a quick look at that. When we talked about this, we said that, like, let's suppose that we have a half-life of 5 minutes. And let's say you've got 20 grams of whatever material it is. Okay, so that would be your amount. And then your original amount, or A sub 0, or A sub O. And let's say after 5 minutes, you're going to find that you're going to lose half of that, so that becomes 10 grams. So that is half-life number 1. So one half-life, technically. After 10 minutes, you're going to lose half of that, so that becomes 20 grams, and that is the equivalent of how much you, oh my gosh, half of it, not double it, moron, is 5 grams. You have only 5 grams left after your second half-life. And then another 5 minutes later, you're going to lose half of that, so that becomes 2.5 grams, and that'll be half-life number 3 in which that occurs, 3 full half-lives. And then, let's say another 5 minutes, which is be 20 minutes then, that's going to go down to 1.25 grams of the material, whatever that is, and that'll be 4 half-lives, okay? These are amounts. This is the original amount, and this is the amount you have after each half-life, and it keeps going on and on and on like that. But here's the deal. Life isn't so neat. You never look at exactly 5 minutes, or if you're measuring something, it never comes out exactly 5 minutes or 20 minutes or whatever. You have to come up with a process when you deal with ugly numbers, real life numbers. Okay? So, one of the things I taught you back in chapter 14, we're going to use again this time, is the bad banking formula. Now, if you put money in the banks and they offer you a percentage of interest, you're going to gain money. Bad banking formula says, nah, we're going to take half your money away every time period, whatever that time period is. So you have your amount based upon your original amount times some factor. Now, like the banks would be 1 point, like it was 3% interest, 1.03 to the n power. This is going to be just the opposite of that. This is 0.5. You're going to lose half of your stuff to the n power, where n is the number of half-lives. We'll be using HL for half-lives for the duration of this discussion. So let's suppose that you had, say, like 14 grams when you start with 20 grams, and you wanted to know how long it took for that to happen. So 0.5 to the n power. Okay? So we just do a little algorithm, divide by 20, get 0.7 is equal to 0.5 to the n power. Your variable now is in your exponent, so we take the log of both sides. But when we do that, this is the product of two exponents, the log and the n. Log means exponent, please remember that. So this is equal to n times the log of 0.5. So anytime you take a log with the n up there, the n goes in front, and you get log of whatever after that, 0.5 in this case. All right, so now I'm going to get n by itself, so I'm going to divide both sides by log 0.5. And this would give me n is equal to, and make sure you put parentheses around this, and your calculator will give you the first parenthesis, but not the second parenthesis. And you can't cancel out log. Log is not something you can cancel out, so if you're thinking in that direction, stop it. Stop it right now. 0.7, log 0.7 divided by log 0.5, which I should have memorized by now. I believe it's negative 0.301, but whatever. Now I'm just showing off. 0.5. And we get an answer of 0.515 half-lives. Okay? Now, so that makes sense because 7 is between the first half-life, let me hang on here, 14 grams, I'm sorry, 14 grams is not quite there at the first half-life, so we know it's less than 1, so we know that it's gone through less than that. Exactly what it is, we can do this by calculating this right here. Now, n, which is the number of half-lives, is equal to the total time divided by the time of the event. I'm sorry, the half-life. This is the half-life. So the number of half-lives is the time divided by how long it took for half of this to go through. So in this particular case, we have 0.515 half-lives. For this, 0.515. Oh, that's just awful. Looks like I had a stroke. And this is equal to the total time, which we are trying to find out, T sub total, divided by the half-life. Well, the half-life we said is 5 minutes. So if we multiply it by 5 minutes to get that by itself, and their T total is equal to 2.58 minutes. This is minutes per half-life, is the label there, and that's why the half-lives cancel out. So anytime you have half-life, it is minutes per half-life, not just minutes. That way the labels half-lives will cancel out, and you have your final answer of 2.58 minutes. Let's take a look at one of the examples I gave you. The example was you started with 9.5 grams of a substance, and it went down to 1.25 grams in 45 seconds. So the question is, what is the half-life? Well, you go back to your bad baking formula, plug in 1.25 here, 9.50 here, times 0.5, the n power. Get 0.5 the n power by itself, so you divide by 9.50, get 0.132, because 0.5 the n power, that's gone. Now you take log both sides, and remember, we do that so we get the n out of the exponent here. And so this becomes n log 0.5. And then we take log 0.132 and divide by log 0.5 to get n by itself. And we get 2.92 half-lives. Now we go to the half-life formula, the n formula, which is the total time divided by the half-life. Well, we said the total time is 45 seconds. We know the number of half-lives is 2.92, so we can calculate the half-life by switching these two. Algebraically, you can do one of two things, put a 1 here across, multiply and divide, or just switch these two around, because that's in the end what you're gonna, is gonna happen. So you take 45 not liters, what am I doing here? Seconds, It's like I'm on the keyboard and I hit the S instead of the L. It's the same finger, but that doesn't make any sense when I write it, so who knows. Anyway, divide these two out, get 15.4 seconds per half-life. All right? Second example I gave you, we start with 28%, or we end up with 28% of a substance when it's done decaying, and that happened in 1.97 seconds, so obviously it was done with a stopwatch. My gosh, that's a fast reaction. Question is, what's the half-life? Well, the question also is, what was the original amount? Well, you end up with 28%. Everything starts, if you look at percentages, everything starts with 100%. So that's your original amount. So we go back to the same formula we did in the last example. 28% is the amount, 100% is the original amount, times 0.5 to the n power. Divide both sides by 100%, you get 0.280. Take the log of both sides. Again, we do that to get this n out of here and put it in front. Divide by log 0.5 to get the n by itself, and we get 0.475 half-lives. Now we use the half-life formula, which is the total time divided by the half-life time. So that's going to be 0.475 half-lives, your n, is equal to the total time, which was given as 1.97 seconds, divided by the half-life. So again, switch these two around, 1.97 seconds over 0.475 half-lives, and your answer is 4.15 seconds per half-life. All right, practice problems. With my slow smart boy is so old and slow. And any minute now, oh, there we go. Okay, great. So, practice problems, 5 of them, and have fun.